it's a great pleasure for me to be there, at least in distance. It reminds me 30 years ago when I used to come sometimes.
Yes.
And it was a very good moment with a lot of friends. Unfortunately, many of them has passed away. But I kept all the good memories of them, and it was a great moment for me. And okay, I'm going to speak of, as you see, the title will be a question of looking for nonlinear elliptic equations, and I had a potential, which is a measure, and it acting on the nonlinear terms. This is a joint work with Nicolas Saint-Dié from Universitat de Buenos Aires, and it does appear in the Annals of Laurent V this year. We consider omega to be on the C2 domain. Sigma is a non-negative quantum variable. And is a continuous absorbing function. That means that G of R is not negative for R large enough. And the typical example, G of R is R to the P minus 1 times R. Or G of R is sine of R exponent times exponential of alpha R minus 1. And now the question we consider is minus Laplacian of u plus G of u times sigma, and with a zero boundary condition. Mu, what is mu? Mu is a measure also. It's a random measure in nonlinear. So what is the meaning of this formulation? We want u to be an L1 function. We want rho G of u is in L1 of sigma, where rho is a distance to the boundary. So this is an important fact is about this the constraint rho G of u is in L1 for the measure sigma. And now we want this formulation, this equation to be written in a very quick sense. That means integral of minus integral of u Laplacian of zeta plus G of u zeta de sigma is integral zeta d mu for all sigma for all zeta in the space of test function, which is just w1 infinity 0, such that the Laplacian is in L infinity. We call it a very quick solution. Okay, now, first, a little of history about this type of problem, which go back in the nonlinear case almost 45 years ago. And in the case sigma equal 1, there were very classical works by Benillan and Brezist called subcritical case with a general nonlinearity. And their theorem essentially is the following. You assume that n is bigger or equal to 3. G is a continuous, non-decreasing function, vanishing at 0, and assuming an integral condition, which is this one, is integral of 0 to infinity of G of t minus G of minus t times t to the minus 2 n minus 1 of n minus 2 dt is finite. Okay, it may look a little strange and complicated, and so it should be the integral between 1 and infinity, not 0, because there is a singularity at 0, sorry for that. Then, if you take any bounded measure of mu in omega, there exists a unique, very weak solution. That means a function with G of u is L1, such that minus integral of u Laplacian of zeta plus G of u zeta is integral of zeta d mu for all zeta in x at omega. Okay. This is this result. You will see that it is rather natural to have this type of integral condition. Integral condition, which is a sufficient condition, but it will come from the construction that we'll see in the case where there is a measure. It's very natural. And it was I think a great discovery of Benillan and Brezist to have this type of condition. Now, if G of R is R to the P minus 1 times R with P positive, then the condition, the integral condition is satisfied even only if the exponent b is less than n over n minus 2. And Medina and Rezis in 1977 proved that for a Dirac mass it was not possible to solve the problem for b being in the harmonic n over n minus 2.
Вот прям секунду, да, секунду, я тебе сразу все присылаю. Спасибо. Так, у меня звук потом. Так, у меня компьютер сдох. У вас перезагрузка. Можете нажать? Загрузить. Это классика. Ну, это там висит, да, все? Висит. Ага, там все идет. Ну, ничего не сложится. Там все идет. Только у нас записи.
Не слышно его?
Что судьба покажет?
C2p prime, which correspond to actually to the topological capacity. That means that if the capacity, the C2p prime capacity of the Borel set is 0, then the measure must be 0. So this is the spirit of all the case of for solving this problem. In the case there is no potential where sigma is 1. Okay? Yes. No. You listen to me?
Yes, yes.
Okay. Just one. Okay. Now notice that if p is less than n over n minus 2, only the empty set has 0 C2p prime capacity. This is due to the fact that by duality, the space C2p prime of 0 is embedded in this conformal part. Now the case when n equals 2, of course, this type of this type of result doesn't work. And there was a very nice extension by Vasquez. And in that case, the model case is linked to the exponential of the function, like g of r is exponential of alpha on this one of r, alpha equals at 0, and the rho is linked to the exponential orders of rho's of g, and we will see later on. Okay. Now, when you look at the problem, initial problem 1 with a sigma is a measure. Now you need to add a framework. The framework is, for the type of measure we can deal with, is we need to produce the Boring classes of measure. And we say that a measure, this measure is, this class is n over n minus theta plus, because they are positive. And with theta is between 0 and n. We say that the measure is in this class n plus over n minus theta if the measure of a ball, or the sigma measure of the ball, is bounded by c r to the theta, or something. If you make comparison with the case, extreme case, theta equal n, then in that case m infinity is equivalent to n infinity. And if theta is 0, m1 is more or less L1. And now in the general case, notice that the space, the Laurent space or Marcinkiewicz space L of n minus theta infinity is embedded in the modulus n of n minus theta. This is just remarks. Okay, there were many properties of Borel spaces which can be found in the books of Anas Edberg, Mazia, and Weibel, in connection with potential and with special potential. And I just give some examples of results which are there and which will be useful in this period. If you assume that n is bigger than alpha p, and 1 is less than p is less than q is less than np over n minus alpha p, then the sigma, the LQ sigma norm of I alpha convolution with F is bounded by C of E, C times F and P, for all F in P, if and only if measure sigma belongs to the Borel class R n R plus of Rn with 1 over R is Q over 1 over Q minus 1 over P plus alpha. This is that result. Now based on now for the Bessel potential, you have this type of estimate that the mapping F maps to G alpha. G alpha is a Bessel potential on the alpha. The G alpha convolution with F, and if this mapping is a linear mapping, continuous linear mapping from LP of Rn to LQ sigma of Rn, if and only if the measure of a compact set K to the 1 over Q is bounded by the capacity C alpha P capacity of K to the 1 over P. This is the Bessel capacity case, and this is also equivalent to the sigma of the ball PR is bounded by C3 times the capacity of the ball, the C alpha P capacity of the ball PR to the Q. These are some results which can be, this type of result which can be used. Now what is the main result? I call it the subcritical case. The subcritical case, you assume that you have a measure sigma is m plus over n minus theta with theta G to be bounded from above by some function gt of absolute value of R large enough. And now the integral condition of Milan and Precis is replaced by the integral from R0 to infinity of gt to the t times t to the minus 1 minus theta over n minus dt is equal to is less than infinity. Okay, if you make theta equal n, that means that essentially sigma is equal to 1, then you recover, of course, the condition of the Milan matrix. Now, if this integral condition is satisfied, then for any bounded random measure mu omega, there exists a very weak solution to the initial problem that we gave before, that it's a problem with boundary data 0 and measure inside. And furthermore, if G is not decreasing, then the solution is unique. I call it mu. Furthermore, the mapping mu maps to mu is a stable from weak convergence of measures L1 of R. So this is the result concerning the subgroups. Now, if gt of R is R to the P, then the condition is that P is less than theta over n minus 2. Remember that theta is between n minus 2 and n, strictly bigger than n minus 2. So you can reach it theta a little bigger than 1 if, for example, when your theta is approaching to n minus 2. A very important case is where sigma is a surface measure of a C1 hypersurface sigma in omega. In that case, theta is equal to n minus 1. And now the condition is that B is less than n minus 1 over n minus 2. And this is very important for applications. It's like the case where sigma is where the measure is just the surface measure. We have also example with fractal measures. What is the main estimate? The unit is called now estimate of Bresis type. This estimate of Bresis type is a kind of an estimate of function when it is in L1. You assume that the sigma is in the Moré class n over n minus theta, always with theta is between 2 and n. G is absorbing. Then for any mu in L1 row, I don't put the right-hand-sided measure, but I put it in just a space of function. Then there exists a very weak solution to the problem. And if G is non-decreasing and U prime is another very weak solution with data U prime in L1 row, then you have this estimate. This estimate is minus integral of absolute value of U minus U prime Laplacian of theta plus integral of omega of absolute value of G of U minus G of U prime d sigma is bounded by integral over omega of U minus U prime, absolute value of U minus U prime. And now you can replace the absolute value by the positive part. And this is valid for any test function zeta in x plus omega. That means that the test function which are positive, W1 infinity 0, Laplacian L infinity, and which are positive. So this is called estimate of Bresis type, which goes back also to the problem with that time in L1 were studied by Bresis, I think, in the early 70s. He has an example, but with also constant notation. Now, third lemma, which is important in order to speak of the integrability. The main problem when we are going to make approximation. The main problem is to prove by the approximation we are going to have. Remember that we have the G of U integral of U of U d sigma. So we want to be essentially G of U d sigma to be G of U to be measurable with respect to the sigma measure, which is not so easy. And this is one of the problems that we encounter. So a result can be found in the book of Adams and Berg, that if U n is bigger than P is bigger or equal to 1, you take a measure sigma in n plus of n minus theta, that case with n bigger than theta is bigger strictly to n minus p. Then the measure sigma vanishes on Borel set with W1p capacity 0. Car 1p is a classical W1p capacity. Okay, this is something that we shall use in order to justify some when you go to the limit. So we need first we have to approximate. So to approximate the problem, we have to go back to simple variational approach. I define the set Wg of omega, which is a set of functions in W1 to 0 of omega, such that capital G of V is in L1 sigma. So what is capital G? Capital G is an integral from 0 to R of G of SDS. That means that G prime is G of R. Okay, so this is the space I'm interested in. And now if sigma is in the space, in the Morris space n over n minus theta with n bigger than theta bigger than n over 2 minus 1, so I have a larger domain. Then for any mu in the space w minus 1, 2, there exists a function u in wg of omega, which minimizes the problem. And furthermore, u satisfies what I looking for, of course, of duality between w12 and w120 and w minus 1, 2. This is the looking for. Okay. So this is the starting point. Now we want, so we have this estimate just by complexity or asymptotic complexity. And now we assume first, now we want to have to construct approximation. You will first assume that G is bounded. Then G of E is in L1 of L1 sigma for any V in W120. Note that it is very important that we know that G is capital G is a function and unbounded because little g is bounded. And we use, of course, the fact that a set with C12 capacity, C12 capacity 0 is neglectable consequence. Now, the function capital J, which is antiderivative, which is my this is my capital G in that case. The capital J is C1 tends to infinity. So a minimizing sequence W1 to 0 is at the relatively compact in N1 and sigma intersect with N2. So it converges quickly to W1 to 0 and it converges up to a set of cap 1 to 0, almost everywhere. Hence, because of this, it converges all sigma almost everywhere. So in that case, we have G of U and G converges to G of U is in L1 and C. Hence, at the limit, G of U is a minimizing capital of J. Now, if J is unbounded, in that case, we write J as J1 plus J2, where J1 is J restricted to the interval minus rho 0, rho 0, and J2 is J on the remaining of R in R times minus this interval. So J2 is monotone and J1 is bounded. Then I write now capital J, capital G is G1 plus G2 accordingly. Capital G1 is just antiderivative of G1 and capital J2 is an antiderivative of J2. So in that case, J1 is sublinear and J2 is non-negative. Now, if you go to the, if U n is a minimizing sequence of the corresponding functional J, then J1 of U and K converges to J1 of U in L1 of sigma because of the same reason as above. And now for J2 of sigma, we use just Φ2, and that where integral of J2 of U is less or equal to the limit of integral of J2 of U and DC. So that means that U is minimized. So now, so we have the estimate we have the constructed solution in L2. Now we have to go to the L1 framework. So L1 framework is the problem, as in many problems, is to go to the limit in the where the priori estimate we will have them easily. The problem will be to go to the limit in the nonlinear terms. And it was a discovery of Pendular and Bresis in the simple case where sigma equal 1 that it is linked to the use of Vitalis theorem. Okay. A simple lemma, which I think is very useful for application now is we take sigma to be a measure in n plus over n over n minus theta, with n bigger or equal to theta bigger than n minus 2, h, the function h such that h times h times is h is an infinity for the measure sigma. F is a function in S with S bigger than n over n minus 2. Then, and you look at the function which is W is the green potential of F minus H of sigma, H sigma. Okay. Then you know in that case then W is continuous in omega bar, and for all the gamma in C2 of R, which vanish at 0, and if J is an antiderivative of gamma, then we have this estimate. This estimate is minus integral of G of W Laplacian of theta plus integral of omega gamma of W H a sigma is bounded by integral of gamma of W theta f dx. This is valid for any test function which are in this space. Okay? You hear me?
Yes. Yes.
Okay, that's good because I don't see the audience. So sometimes I am checking that my connection is good.
Yes, the connection is okay.
Yes, okay, that's good. Okay, just a minute. I have to put my battery. 1 minute, 1 second.
Okay.
Sorry.
Слайд не нужен?
Пока да.
Нужен или не нужен? Нужен.
Почему я не могу? Что ты можешь? Он куда-то ушел. Слушай, я не могу полноэкранный режим сделать. Представляешь?
Дабл укрепление экрана, там больше стоит.
Почему не могу туда влезть?
Потому
что и подумать.
So you see when you have an old computer, the battery is not very strong.
Yes.
Okay, so I continue now.
People are stronger.
A consequence of this is that you take now of G the absolute value, and you have the minus integral of the absolute value of U W Laplacian of theta plus integral of omega, the sine of W H theta a sigma is bounded from above by integral of sine of W theta f dx. Okay. So this is a key estimate in order to reach a priori estimate for the problem. Now we use Brazil's method. Brazil's method is, okay, we approximate mu by UN, Mu's function, and we have UN is the approximate solution. We have all the a priori estimate of UN, and in particular, what we get, we know that UN is going to be bounded in relatively compact in L1 of omega. G of UN is bounded in L1 of sigma, and this is because of the a priori estimate that we have, the inequality we have before. So the main difficulty is to prove the convergence of G of UN is in L1 of sigma. So for that, what we define, okay, I'm going to set, I define the set A lambda of mu is a set of x in omega such that the green potential of the absolute value of mu is bigger than lambda. remember that also that a solution of even of my approximating problem is essentially bounded from above, in case the measure is positive, if the measure mu is positive, is bounded from above by the green potential of the measure, because it's a problem with absorption. Okay, this is a key point. This is a very important factor. And now, if I define the set capital E lambda of mu by this one, now the sigma measure of this set is little e sigma of mu. Okay, and what we know, because of the estimate, classical estimate of G of a measure in a space L1 of sigma, so we know that going G of mu, if mu is in a measure, G of mu will belong to some Lorentz space, which is going to be the Lorentz space N over N, the Lorentz space L theta over N minus theta. So that means that the measure, the sigma measure of the set, this set here, because of the Lorentz space, space, is bounded by C times, some constant, times the measure, times the lambda to the minus theta over N minus. Now in order to prove, okay, we know that the G of UN is converging almost everywhere, and sigma almost everywhere. Now the problem is to prove that we can use wave convergence in L1 sigma. So for that I use Vitalis theorem, and I set E is a Lorentz set, and I write the integral of G of U, absolute value of G of UN d sigma, is bounded by G tilde of UN, because this is my estimate here, on the set E. And now this integral, it's smaller than integral of capital E intersect with UN bigger than lambda, plus integral of capital E intersect with UN less or equal to lambda. Now, this term here, I know that it's going to be bounded by the sigma measure of the set times G tilde of lambda. Now, for this, just I use the integral with respect to the measure, because I know that UN is bounded by, UN is going to be bounded by G of mu of the measure UN. Okay, so I just make integration with using the measure of the set where UN, or if you want, even where G of UN is bigger than lambda. So I have this term here. I make integration by part, and what I obtain exactly the condition that I want. Okay. Now, if E sigma, first I fix now I fix first lambda such that this term is less than, for epsilon given I fix lambda such that this term is smaller than epsilon 2. And for lambda fixed now, I take the measure E sigma to be smaller than epsilon, so that this term is smaller than epsilon 2. And then I can go to the limit by Vitalis. Now, what happened in the 2D case? In the 2D case, essentially, well, I recall what Pascal did, it was a great idea, that if you have a function f, it is natural to compare its growth with respect to the exponential growth. Because when n equal to 3 or larger to 3, the comparison is with power. When n equal to, the comparison is with exponential. So it defines a infinity of f is the infimum of the number alpha positive or non-negative, such that integral from 0 to infinity of f of s exponential of minus alpha s ds is minus. Okay, so and you have an expansion of minus infinity. Now, for example, if f of r is r to the p minus 1 times r, then a infinity of f is 0. If f of r is exponential of AR minus 1 or A positive, then A infinity of F is capital A, and A minus infinity of F is 0. Now, if F of R is sine of R exponential of R squared minus 1, then A infinity of F is plus infinity, and A minus infinity of F is minus infinity. So these are examples. And okay, when J is non-decreasing, we define this here. You can extend this, but I think it's just it's a technical story. And what is the theorem? The theorem is the following. We assume that N is 2. Sigma belongs to the Moré class N plus 2 over 2 minus theta, with 2 is bigger than theta is bigger than 0, and J is absorbing. Then if A infinity of F is A minus infinity of F is 0, like for power, for example, then for any mu model, you have a very big solution. Now, if A infinity of F is positive, but finite, A minus infinity of F is negative but finite, then there exists a delta positive, such that if mu is in this class is a bounded measure, and if the norm of mu in the class F is smaller than delta, then there is a solution. Okay, this is probably is not the optimal form. Probably it should be improved, but it should be very technical. Because what is important in order to disturb the problem, to make difficulties, is a singular part of the measure, not the regular part. I will discuss on this. So probably it should be improved, and actually Vasquez's result was with a case sigma equal 1, and he has a very, very sharp estimate the case to notice, okay, so I go to this. Now I want to speak a little about the super critical case. First, we notice that G of mu plus is a super solution. We assume that, for example, I assume that the case that G is absorbing, that R0 is G is positive on 0 plus infinity and negative on 2 minus. Okay, this is for simplicity. Now you take a measure sigma. You assume that sigma is in this Moré space. It should be n over n minus. Now with theta, that case is between n and n minus n over n minus 1. So there is a restriction. Now if mu is bounded, and if rho G of mu is in L1 of sigma, then this equation admits a very good solution. Now, if, what I told you, if G satisfies the delta conditions, that means the absolute value of G of R plus R prime is bounded by A times absolute value of G of R plus absolute value of G of R prime plus E. Then you don't need to have a whole estimate of rho G of G of mu L1 of sigma, just only on the singular part. So you compose the measure mu as mu singular plus mu regular with respect to the n-dimensional Nobel measure. And if you have that the rho G of mu of J of the singular part of the measure is L1 of sigma, then there exists a very good solution. Well, this is some sense, it's a natural extension. Okay, now you want to characterize measure when G of R is bounded by C times R to the Q plus 1. Okay? Then you have a characterization that if sigma is n plus over n minus sigma, with n bigger than or equal to capital theta bigger than n minus 1, and g of g is not decreasing and satisfies this estimate, this growth estimate, then you assume that you have a p bigger than 1, s bigger or equal to 1, such that n is bigger than sp bigger than n minus theta, and theta p over n minus p is bigger than g. Then if mu is absolutely continuous with respect to this capacity, then you have a weak solution. Okay, this is a bit complicated. This is a very technical and probably not optimal. But the only interesting case is that theta equal n. We can take p equal q. Okay. And then we recover the balance. What?
No.
Okay. Now a question, okay, these are sufficient conditions. Now if you want to have necessary condition, we define the capacity which is called a two-plated type capacity. And it is defined by the following form. If you take the cap sigma p of E is the infimum of the integral of omega over the E prime E sigma for all the V in L P prime of omega, non-negative, such that J of G of V sigma is bigger than equal to 1. And okay, now in that case what you need is to have a measure which are theta regular. And what is a theta regular measure? That is essentially that the measure of the ball PR is comparable to R to the theta for all the x in the support of the measure. For example, of fractal measures or the measure of n-dimensional compact manifold. This example. So in this framework of measure, we can have a necessary condition. The result is the following. And you take a sigma measure in the space n plus n minus theta. Okay, with theta with n bigger than or equal to theta bigger than n minus 2, you assume that it is theta bigger. Then if you can solve the problem with a measure, bounded measure, with g of r is r to the pi minus 1 times, no, it should be r here, I'm sorry, g r to the p minus 1 times r. Then if there is a solution, then we know that this measure is going to be it's going to be absolutely continuous with respect to the capacity that I just defined. Okay, it's not completely surprising because remember that the result of Barras and Thiers, they were necessary and sufficient conditions in order to solve the problem. So it was a very strong result, and it's natural to find a series of necessary conditions. Okay, these are essentially the results that I have, and I would like to discuss about some applications because there are many applications which are very interesting. Okay, first observation is the following. You look at this, the problem. You want to solve this problem, find an harmonic function in omega, which satisfies this condition du over dn, not in omega, this is in the half pole, positive half pole. P1 plus, P1 intersect with R plus. With satisfying this condition, the boundary nonlinear condition on the boundary. Okay, on this boundary, and which vanish. Okay, which vanish on the remaining part, the upper part of the domain. So on the lower part of the P1 intersects with Rn plus, you have this condition, and you assume that it's 0 on the upper part of the boundary, where you assume that U is a even measure on the sigma part of measurement sigma. Now you look at the even extension U tilde of U B1. I mean, just to say that on one side you make just a simple extension by symmetry with respect to the plane, with respect to the higher plane exponent. Then what you find, which is very interesting, that you find this problem minus the fraction of ut plus twice g of u, d sigma equal to ut. D sigma is a surface measure on this one, on d1 intersect with d1 plus. And now you call mu d just an extension of u by 0 in d1. So that if you want to solve this problem, you are reduced to solve this problem. Okay. And conversely, since you solve this problem here because of uniqueness, you have a US solution which is necessarily even, and then it satisfies this. So that means you can reduce a problem, this type of problem. I think in Lyon's book, I believe this type of problem are more or less called transmission problem, but I'm not sure. Maybe people working in mechanics know this type of terminology. Now you can of course extend it with the Laplacian. The Laplacian, these are work which are progressed. So what is the condition? Condition, you can extend completely this problem, the problem that I've given before. Instead of minus Laplacian of u plus d of u sigma is u, you can replace the Laplacian by minus delta t. Okay. Now, the main difference is that very weak solutions are replaced by a normalized solution. The framework essentially remains the same, the subcritical case, and there are many preliminary results by a former postdoc from me with this Konstantinos Fikas. The University of Athens. Okay, and what is a tool? An important tool if you want to handle this, to go back like in the Bresis, Denilan, or Barras story, in the case equal 2. This is to look at what happened, what was the structure for solving the case sigma equal 1. Okay, and in the case sigma equal 1, there are many works that have been done by Veron L and myself, published in the journal okay. And in that case, you have to replace, of course, the tool is a green kernel, but you replace the green kernel by the Wolf potential. Wolf potential plays the same role, and you have also a notion of subcriticality and supercriticality, which is exponent here. Extension. Also another extension, which is the following. It is the following. It's a case minus Laplacian. Look, it's extension of problems that are given with the case equal to before. So minus take a p-harmonic function Rn plus, satisfying this boundary condition on the Rn minus 1, this boundary of Rn plus, and you assume that it goes to, well, I don't understand what is this condition. But on this condition is not good. Okay, this side you don't have this condition, that's not upper bound, it is upper. Okay, only look at the two first conditions. This one, and this nonlinear condition, which is the main one, minus delta u to the p minus 2 du over dr plus g of u. So in that case, you make the same story of even extension. And then you use all the estimates which are used by either the subcritical case, which were done by by Dalmasso, Laurent V, maybe I forgot one. And in the supercritical case, we use a technique produced by Veron and myself. And it was a PhD thesis of that I given that was published in other studies. Okay, I just given now a series of output extensions because I have to be what happened when you put the right where G is not an absorption, but it is a source. So much work has been done by Jai and Verbitsky. There is a very lot of papers by Jai and Verbitsky, but the approach is completely different. But you see that the function, in that case, for example, is mu is positive.
is P superharmonic, so when P superharmonic instead. Okay, another extension which has not been done is just to look at the parabolic problem. So you look at the parabolic problem, dtu minus Laplacian of u plus d of u times sigma is nu in omega times 0t. U vanishes on d omega times 0t, and the initial value is null. Okay, this is another problem which could be interesting to study. And just I would like to finish a little. Question is about to analyze the notion of trace associated solution, a positive solution of this type of equation. So what is a trace? Is a question of boundary trace. Boundary trace, you look at any positive solution of minus Laplacian of u plus d of u sigma in omega. No boundary condition. And you can also associate, there is another problem which is interesting, it could solve the problem with a boundary condition, the matter with a condition, with possible condition on the boundary. Okay? This is the condition, boundary condition. And so the first, what is a notion of weak solution of the first problem? Well, just that g of u is in L1 sigma log. U and u is in L1 log, and then you have the estimate, the previous estimate, for all test functions with compact support. X of omega in that case have to be taking function with compact support because we don't go up to the boundary. Okay. So this is the notion of what is a very weak solution of this equation. Now for the equation of this problem is just that you want if you want to speak of this problem, then you want to say that the solution is in L1, rho of G is in L1 of sigma, and you want the problem to have boundary that just by integration by part as this classical. So my question is classical case with G of G is UQ minus 1 times U. And many work has been done by Marcus and myself in the past 20 years. And the question is the following. I'm going to give you two problems. Find condition on the measure sigma that any positive solution admits a boundary trace. And it was shown by Marcus and myself that the boundary trace is not, if Q is bigger than 1, the boundary trace is not necessarily a random measure, but it is a coherent measure. That it can be infinite compact set of the boundary. And we have a whole description, we have a book on that. Okay? And an equivalent find to see that the boundary trace is a coherent measure is equivalent to have this type of dichotomy. The dichotomy is the following. For any a d omega, the following dichotomy occurs. Either there exists theta positives such that u is in L1 of omega intersect with b theta of a, and rho times u to the q is in L1 sigma of omega intersect with b theta. This is a case where there is a random trace, or for any theta positive, integral of u plus, or it could be u d sigma, u dx plus u q d sigma is on the omega intersect with b theta. Okay. This is probably the dichotomy which makes a difference, which could be, but it's a conjecture, of course. The dichotomy should be this one, but now proves this equivalence with this condition and the dichotomy. This is a problem of the whole story of the boundaries. Okay. And for my 126 is this one. Okay, for this problem with boundary parabolic measure, so the question, find a general integral condition for the solvability of this equation with any bounded measure on the boundary. This is something which has been done in the case of boundary measure when sigma equals 1. It was a fourth paper that I gave a group with IFR in 1980. And in the case of power, that probably has condition on the condition for the solvability of any measure. Okay, this is a very simple observation. If G of Q, if G of R is dq of R, that means R to the Q minus 1 times R, should be less than 1, then you have always that you take the Poisson potential of the measure U, you take the power Q, and you take the measure. If this expression belongs to L1 of sigma, then you can prove the reason of the problem is solved. So this was
And what is about unique or unique?
uniqueness comes only from monotonicity. When the G is monotone, there is uniqueness. It's a problem, it's a monotone problem. So uniqueness is not a big problem. It's not when G is monotone, uniqueness is guaranteed. But when G is just a general absorbing nonlinearity, then you are not sure, of course, that there is uniqueness. In the case you may not have uniqueness. But the difficulty is not uniqueness, this type of problem. It's a question really of existence.